Hola, Carmen.
Vale, perfecto. En principio, ¿se ve bien?
Sí,
Perfecto.
bien.
Hola, Carmen.
Perfecto, perfecto. No sé si os puedo mover un poco hacia la derecha. Vale, perfecto. Si me tapáis un poco ¿se ve bien? Vale,
Sí.
un poquito.
Bueno,
Muy bien.
suprimiremos el vídeo
No sé si os
luego.
puedo
Sí.
mover un poco hacia la
Vale,
derecha.
vale.
Vale, perfecto. Si me tapáis un poco ¿se ve bien?
Ahí de protagonista. Bueno,
Muy
suprimiremos
bien.
el, suprimiremos el,
No encuentro
el
unas
vídeo
gafas que
luego.
tenía
Sí.
antes. No sé en dónde os he dejado. Y es que es
Ahí de
un rollo.
protagonista.
Es absolutamente un
Bueno.
rollo que te pones así y no hay manera de fijar la vista correctamente. Es terrible.
Yo me he hecho unas progresivas, yo no tengo nada, yo veo perfectamente de lejos, pero me he hecho unas progresivas
No
para
funciona.
poder estar con las gafas puestas todo el tiempo y no estar quitándomelas y poniéndomelas.
No, estas son progresivas y es horroroso. O sea, ahora no veo nada. Es que no veo nada, nada de nada. Es que no me acostumbro en absoluto.
Opérate.
Me da miedo, me da miedo.
Qué miedo. Está ya todo muy bien.
Ya, pero no sé. No. Me da miedo. Ya he pensado a veces, pero no me atrevo, sinceramente.
A ver, solo huele a carne quemada un rato.
Vale.
Y es la tuya además, ¿no?
Me estás convenciendo muchísimo ahora. Vale, pondré mi cronómetro, así también tendré idea del tiempo. Ya le he dicho a Inma que he mirado el tiempo que tardo más o menos y tal, y solo me paso 3 minutos. 3.
Bueno.
Ya le he pedido bula por 3 minutos, pero y basta. Digamos,
No pasa nada. Hemos tenido algún seminario un poco más largo.
Y ya me imagino. No, es que es complicado, es complicado.
Sí, por supuesto.
Más que nada porque he tenido que introducir una parte más introductoria y eso me ha hecho, entonces tengo que eliminar otras cosas, entonces
Claro.
tengo que reajustarlo todo para que en el tiempo acordado.
Bueno, no te preocupes.
Vale.
Voy a empezar, si os parece, a grabar, luego ya lo recorto cuando lo suba, porque es la hora. A ver si...
Grabo yo también, ¿vale, Isidro?
Vale. Espérate.
Okay, I guess we should switch to English, right?
Yes.
So we are 24 participants. It's 12 o'clock. Shall we maybe wait another minute?
It's 12 now.
Yeah, it's 12 now, yeah. So
Uh,
we wait another minute and see if more people connect.
the YouTube channel is not working.
Oops.
Who is in charge of the YouTube?
Sean, I'll check with him right, offline.
Okay, if you agree, I would propose to slowly start.
Slowly or fast?
Yes. Well, let's start slowly and then. So so welcome everybody. So today we have Joaqim Matias. Let me just briefly mention some short introduction. So he's a full professor at the University of Barcelona,
No,
Autónoma, and he obtained his PhD at the UOB, at the Universitat of Barcelona. He spent several years as a postdoc in several places, in Padova, in Trieste, also at CERN, and also in Aachen. He got several fellowships, including the Marie Curie, Ramon y Cajal, and also the I3. He is an expert of several scientific organizations. He's also Garante of the IFAE Severo Ochoa. He has given plenty of talks, also organized conferences and published outreach in different journals. And today he was also awarded for his research that led to the identification of the well-known B-Flavour Anomalies with the ICREA Academia Prize. So we are very pleased today to have him describe these B-Flavour Anomalies, including the status of the global fits, the next steps, and also a new non-leptonic anomaly. So Kim, whenever you like, the floor is yours. Thanks for agreeing to give this talk.
Okay, so first of all, let me thank you very much to the organizers for the kind invitation to give this talk here. Indeed, I was asked. Oops! Oh no, this is the problem. Okay, fine. So I was instructed by the organizers to try to be as pedagogical as possible, at least at the beginning, in such a way that I can give you the minimal ingredients so you can understand more or less what are these anomalies that people is talking about, mainly in the flavor sector. Then I will discuss the diagnosis of each of those anomalies, which is the situation of each of those, how we treat them. Then I will discuss briefly the uncertainties that affects those anomalies. I will tell you what is the present situation of the global fits, the results, the outlook, and also what else. What are the next steps from my personal point of view. And finally, I will discuss a new B-Flavour anomaly that I think it has not received the attention it deserves. I think that's a very interesting one. And then I will conclude. So let me start with some motivation. So you know that standard model has been tested many, many times, and in all cases, it has been an extremely successful theory that has passed all those tests. However, we are sure that this model should be taken more as an effective theory that belongs to a more fundamental theory, because it cannot explain several things. For instance, why there are 3 generations of fermions, why the masses are so hierarchical, why we are here in this talk. In other words, what is the origin of the baryon asymmetry in the universe? That because the standard model is not able to generate the matter-antimatter asymmetry, and without that, we could not exist, and we could not be in this seminar. Then there is the lack of a candidate of the dark matter observed in the universe. Also, the gravity is not inside the standard model. So for all these reasons, a more fundamental theory with new degrees of freedom, but also new properties, and this is many times not enough emphasized, should be uncovered at some point. Okay, so also new properties. This new theory defines what is usually called new physics. And as you know, there are basically 2 ways to search for new physics. One is the direct production of new particles that belongs to this new fundamental theory. So far, besides some ghosts, we have not found anything, and except for, of course, of the standard model Higgs. This direction needs energy. And then you have a second direction, which is the indirect searches, in which these new particles, you produce them virtually, and they affect the couplings and the decays of known particles. This second direction or approach, indirect searches, give you access to energy scales much larger than the direct searches. And in that sense, I like to always say that this is more frontier research in direct searches than direct searches, because it's natural to see new physics effects first in indirect searches and later on in direct searches. So this is the approach of flavor physics. And these are our tools. These are the particles that we know how they should decay in the standard model. And by looking at deviations in the way they decay is the way we try to disentangle and identify new physics. The BS meson, the BD meson, and the charge mesons. Here I'm giving you all the properties of these particles just for the record. Now, what is the interest in flavor physics, at least for this talk? What is our target? Our target is those processes in which standard model new physics can compete. So basically, those are loop-dominated processes in which the standard model is forbidden at 3 level. And those, an example of those kind of processes are the flavor changing neutral current processes, so-called also rare processes. These processes, in principle, can help us not only to constrain, but hopefully also discover new physics. Now, let me give you a first example, fundamental for the discussion that I'm going to do here, of a flavor changing neutral current process. This is the decay of a B0 into a K star mu mu. In that case, you have an spectator quark D, and you have an antiquark B that decays into an antiquark S. This transition here, in this transition, the quark changes flavor, but doesn't change the charge. That's why it is called flavor changing neutral current. And this is mediated by a set of particles of the standard model, or it can be mediated by new particles, in that case, supersymmetric particles, let's say, just to give you an example. So in principle, these new particles will affect the way this B0 decays, and as a consequence, you may detect the presence of these new particles. Now, what is the goal of this talk? Let me just focus a little bit more on what I would like to...
Kim, we're still seeing James Stewart and Grace Kelly.
What? Oh, really?
The transparencies are not changing.
Oh, my God. Thank you. So you are Grace Kelly here. You are here. You have seen this, the B0, nothing else?
No, we are. Your sharing is frozen in slide 3.
No, it's not moving. Okay, it's not moving at all.
That's right. It's frozen. So you might like to unshare and reshare.
Stop share. Okay. Thank you, Santi. So, I can share the desktop. Maybe it will be better. Let me try sharing the desktop. That's why. You can see something now?
No, you are not sharing.
I'm not sharing, sorry. Sorry. Then here, share screen. You see something new?
No, you need to click at share. Even if you did click once, you might like to click second time.
Now?
Well, it's
frozen still.
Yes. Well, at least I don't see. I see still black. You can maybe send the slides to me and I can share them for you. I don't know.
Wait. Stop. Let's do another trial, previsualization. Share. We did the test before and it was working.
It was working, but now it does not seem so.
You see something?
We see that has started screen sharing, but we see no slide.
You see no slides.
That's right.
Now?
No. Unfortunately, it does not seem to work.
Okay, then what shall I do?
You can send the slides to me by mail. I can try to share them.
You will have the same problem, I guess.
Or disconnect and connect again to the
Maybe tool. Also a good possibility.
Disconnect from Zoom and connect again.
Okay, I will do it. Okay, sorry. Stop sharing.
Yes, now we do see the slides, Kim.
Yeah. The question is if you will be able to see it when they move. You see the change?
Yes, now we do see it. Yes.
Okay.
For some reason, it got stuck. I don't know why.
Please tell me if they become stuck at
Yes.
some point again.
Yes.
Okay. Now I don't know the time anyway. Okay. So okay. Let me at this stop at this one, because that's an important one, and then I will continue. So what is the goal, or the initial goal of this seminar? Now the goal is to survive to the end of the seminar. So for the point of the goal, or the goal of this talk, was to see to show you that there is coherence on a large set of deviations and anomalies that we are observing. Okay, is coherence the main message that I want you to bring home. One of the things that we are observing systematically is that nature seems to point towards violations of lepton flavor universality. This lepton flavor universality means, as you know, that the gauge bosons does not distinguish between leptons of different families, and it predicts that the standard model is going to be quite democratic between electrons, muons, and taus. However, what we observe from data is that this is not the case. Now, I will not discuss any specific UV completion in this talk, but my goal will be mainly to show you that there is a signal of new physics. Can you see the next slide?
Yes.
Okay, so the path to the anomalies, okay? So here is what I try to give you some ingredients. So the starting point is this angular distribution of a B to K star mu. This is a four-body angular distribution that is parameterized in terms of three angles that I'm giving you here for the record, and the Q squared, the lepton invariant mass square. This angular distribution is function of these coefficients GIs, and inside these coefficients GI, they contain inside the transversity amplitudes, for instance, perpendicular, parallel, and zero, and left, right, depending on the leptonic current. Now, the important thing for you to remember here is that inside these amplitudes, there is some information on the atomic quantities that you are not interested in, and the Wilson coefficients of the operators that I will discuss in a moment, in which the new physics is encoded. This is the goal, to determine these Wilson coefficients CI. Now, Q squared, the lepton invariant mass square, allows you to separate the spectrum in four regions. The region around the photon pole, the large recoil region between 1 to 8, that corresponds to small q squared, the Charmonian region, and the low recoil region that goes from 16 to 20. Okay, these are the four regions. So when I will talk about large recoil, I will mean this region. When I will talk about low recoil, I will mean that region here. Now, let's go a little bit more in detail, the amplitude of the B to K star mu. How do we describe the amplitude? For that, we use the BS into LL effective Hamiltonian that allows you to separate short and long distances. Now, here you have the Kobayashi-Mascabas, the Wilson coefficient, and the operators OI. The operators, the main operators in the standard model, or in a standard model-like theory, are these three: 07, 09, and 010. By the way, when I move the mouse, you see it?
Yes, we do.
Okay, well, good. Okay, so the one in red, the operator 09, which has a vectorial coupling to leptons, and this one, which has an axial vector coupling to leptons, play one of the most important roles in all this discussion. Now, the coefficients of these operators in the standard model at the scale of 4.8 GeV are given by these values here. For the rest of the talk, you just need to remember that C9 is around 4 and C10 is around -4. Now, in presence of new physics, the coefficients of these operators can get extra pieces, extra information, extra contributions that come from new physics. And this is the goal, to determine this CI new physics here. Besides, you can generate new operators that you don't have in the standard model case, like this 07 prime, 09 prime, scalar operators, or tensor operators. Now, there are basically two sources of atomic uncertainties in the description of this exclusive decay. There are local contributions that describe the transition from the B meson to the M. This is parameterized in terms of these A mu and B mu, and these are the so-called four factors. For the A mu, you have contribution from 07 and 09, and for the B mu, you have the contribution from C10. On the other side, you have also contributions coming from this kind of diagrams that are non-local contributions coming from charm loops. In that case, you have the important thing to remember here is that this kind of contributions enters into the same place as the A mu that is related to 07 and 09. So this charm loop contribution mixes in the same place as these two. And this is part of the problem. Finally, another important thing that I need to introduce is the concept of soft form factor. Now, in order to describe the B to M transition, you can you need a set of form factors like these vectorial, axial, tensors that I will not go into any detail on them. But you can compute them in different ways in the locus region, using like constant rules with Meson distribution amplitudes or like constant rules with like Meson distribution amplitudes. Now, in whatever way you compute them, I don't care, they should, in the limit of m going to infinity and q squared small, they should fulfill these relations here, that all these four factors are related in terms of these two quantities that are called soft form factors. Our analysis should include not only the soft form factors, but also all the other corrections that I will discuss later on. But the important thing is that to remember this, and you will understand in a moment why this is important. Now, this is where you will see it. I mean, in order to describe completely this angular distribution, you introduce this set of optimized observables. Why they are called optimized? They are called optimized because we constructed them exactly in a way that it cancels at leading order the dependence on these soft form factors. Okay, so the core of the information of the four factors that is inside the soft form factors is canceled exactly at leading order in these observables. That's why they are optimized, and that's why they are in a better situation to disentangle new physics from hadronic uncertainties. This is one of the famous optimized observable, which is P5 prime in terms of the corresponding amplitudes. Now you have in principle all the ingredients to be able to understand the different anomalies that enters in here. Let me start with the first one and one of the most important ones, which is the one that has been measured by LHCb, Bell, and Atlas. This anomaly, in which it's found that there is a systematic deviation from the standard model predictions, in particular in the observable P5 prime, the one that I have introduced a few seconds ago in this angular distribution. It shows in two subsequent bins a deviation of 3 sigmas with respect to the data. Okay, these are the so-called anomaly bins. This is an optimized observable for the reason I explained before. Besides LHCb, Bell, and Atlas that has systematically updated, in particular LHCb, the data, now also the chart channel is included, and as again there we see with large errors, of course, the presence of a deviation. Now, as I will discuss later on, we have observed a significant increase of significance of the coherence between this anomaly and all the rest. The only experiment that finds a result which is more standard model-like is CMS. And we talked with the guys that did the analysis, and we observe that they take the correlations from FL and P1 and P5 prime from different PDF, which is kind of risky. So we propose them, we suggest them that in the next analysis that they do, they take them from the same PDF, like all the other experiments does. Moreover, the people from Atlas tell us that people from CMS were using a numerical row fit for 3-dimensional PDF, which again is delicate, okay? So it's much better to use analytical integration as all the other experiments are doing, because you have a much better control, in particular with a problem like row fit. But it's not only that. I mean, we have also a set of branching ratios like B2K mu mu, B2K star mu mu, BS into 5 mu mu. All of them systematically show a deficit in here with respect to the standard model prediction. These observables are much more sensitive to the four factors, like the previous ones. But what is nice is that you have a systematic deviation, and you always see a deficit in all those channels. A different kind of anomaly is the one in which you measure lepton flavor universality ratios, like for instance RK star. In that case, what has been measured is these two bins of RK star. RK star is defined in this way: the branching ratio of B2K star mu mu versus the branching ratio of B2K star E plus E minus. This observable in the standard model is perfectly, I mean, you have a perfect cancellation of uncertainties above 1 GB. Below, you have the dependence on the masses. But in presence of new physics, and this is important I always insist on that point, then you have to have full control of all hadronic uncertainties if you want to disentangle new physics. Okay, that's important. So it's very clean in the standard model, but not so, indeed, not clean at all in presence of new physics. A different issue or different kind of observable is RK. It's also an LFU ratio. Now it has become much more famous because it has passed the threshold of 3 sigmas. And this one, opposite to the previous one, has a cancellation of all uncertainties, not only in the standard model, but also in presence of new physics. Okay. The point is that basically you have 3 form factors and you have basically one that dominates, and being the same in the numerator and denominator, they cancel.
Sorry,
Sorry? Is there a problem? Is okay? Can I continue? Or?
Yeah, sure.
We are seeing a slide 15, or at least me, I'm in slide 15, Kim. I think you have moved on.
Okay, can you see something else, some change now?
Not me, I don't know for the others.
No, no change, still 15.
Still 15, yes.
My goodness, this is a nightmare. What shall I do? No change, no? No change.
This is weird that it becomes frozen in the middle of your talk.
We see this from time to time in meetings. I think it's a kind of bug of Zoom with Max. It's annoying.
Yeah.
So shall I do the same thing again?
Yeah, probably.
My goodness.
So we know the solution.
Stop share. Okay. If okay, let's try again. Share screen. You can see something, some change now?
Well, we see your screen, well, but it's not in full screen, and I don't know.
You're not in full screen?
It is not, no.
I have done the same thing, exactly the same thing as before. Stop share. I will stop share again, and then I will share again. Sure. Now you can see it.
No, it does happen the same thing as it in the past, right? That you were trying to share and we didn't see anything
Okay, let's
appearing.
let's do one thing. Do you have a Mac or not?
Yes, I do.
So you will have the same problem then. Anyway.
I don't know.
I send you the talk, and okay, then you will need to do the work.
I have a PC, Kim. You can send it to me if you want.
Okay. Can you give me your email address? Isidro, is you Isidro who talks?
Yeah, yes, this is Isidro, yes.
Okay, okay. So I send it to you.
Yeah, there is a Arsenal that suggests to use another PDF viewer, but I think you tried, right, with Adobe or with...
No, I use, oh, that's a good point. I use previsualization, not Adobe.
You might like to try Adobe, I don't know.
Let's try for a second. Yeah, that's a good idea. That's a good idea. That's a good idea.
Well, you can also send slides to Isidro.
Yeah, do both things. Just give me a second.
Somebody is also suggesting that instead to use full screen to share the presentation, to just share the screen without do full screen.
I tried it, but it didn't work. I tried only share screen, but it didn't work. Okay, I have sent you to both of you the slides, and I will try again now with Adobe. Let's see. View full screen mode. No, I should go here first. No? So share screen, Adobe. share, and then view full screen mode. Can you see something now?
It's the same problem, right? It's sharing that doesn't work.
Sharing is paused. Bring your sharing.
Yeah, it's not appearing.
No, it gives me a message. Okay, let me try what I was suggested to do. Test 1. In that case, you see something? You see something? No?
Not yet, no. I still did not receive your message. I don't know if Isidro, you did receive it. Now it appeared.
Now I see.
It is working now, Kim.
Yes.
Okay. Yes. Now
we can see your full screen, right? Yes, now we can see your full screen.
You can see it. Wait a second. You can see it now?
Now, yes.
I don't know where I was.
You were, well, slide, I don't recall.
I think it was in here. It was in arcade.
It got stuck in slide 15, I think, and as you move a bit.
But you know, the problem is that. Okay, yeah. Okay, in slide 15, yeah.
Yeah, you were in and you were describing already 16. Yes.
Yes. You can see the changes now.
Yes, as usual.
Okay. That's going to be a long seminar. Okay, I will invite you to some beer afterwards. So, okay, arcade style I already discussed. That is very sensitive to form factor in the presence of new physics, but not in the standard model. In the case of arcade, as I was saying, now it has become more famous because it has passed the limit of 3 sigmas. Trying to move this. Oops. Okay, doesn't matter. Now, the interesting thing is that you know, the standard model prediction for arcade would be 1, while the experimental value is shown here. But is it very interesting that very recently also LHCb has provided some information that didn't provide the previous case, which was the angular distribution of the electrons. And this is very interesting because you can have a number here because of a deficit here and an excess here. So in the 2 different ways. No? So the fact that you have this information tells you that the standard model, that the electron seems to be quite more standard model-like than the muons. And this tells us that the bulk of the effect is a deficit in the muons. Still, you can have some excess in the electrons, but it's going to be subleading in confront to the deficit in the muons. That's an very important information, new from this couple of months. You can see the next one, Q4, Q5.
Yes.
Okay, fantastic. Okay, Imma, be very focused because I mean,
Yes.
Okay, thank you.
There is also lots of focused people sharing in the chat.
Okay. Now, there is an also very important new observable is this observables Q4 and Q5 that we proposed some time ago. That is the difference between the optimized observables P4 prime and P5 prime. These, like in the case of arcade and arcade star, they are very extremely precise in the standard model. They are basically 0 with a very high accuracy because you introduce all the correlations that you know between these 2 observables and you get 0. Okay. Moreover, in presence of new physics, it's optimized. So in presence of new physics, you have the good control of an optimized observable. So in this sense, if you want to kind of classify the 3 LFU observables, you will have arcade as the best, then you will have Q4, Q5 very near to this one, and then arcade star, which is much lower in the sense of interest for disentangling new physics. Besides that, you have the branching ratio of BS into mu that has been computed, has been measured by LHCb, CMS, and Atlas. And they have provided a combined result with a 2 sigma deviation. Now it has been recently updated by LHCb, and this is our average that was provided nicely by Diego Martinez, to whom we thanks. Besides these LFU violating observables, you have in the neutral channel, BS into LL, you have also LFU violation in the charge channel, B2CL new. This is the observable RD and RD star. That's a little bit strange, if you wish, not so natural like the ones in BS into LL, which are loop dominated, because this is a 3-level dominated diagram. And that's not the place where you would expect to see a new physics effect, because This means that new physics should compete with at level. But still, we observe a 3 sigma deviation there. And okay, we should see how the data will evolve with time. Now, atomic uncertainties. This plays an important role, and you have to have full control of them in order to make sure that you have new physics in front of you. There are 2 types of new physics that I have already mentioned very briefly at the beginning. 4 factors. You have 3 form factors for B2K transitions, and 7 form factors for B2K star and BS into5. At low recoil, lattice QCD, you use, at large recoil, you use like constant rules, P-Meson or like Meson distribution amplitudes. Here I'm giving you an example of 2 computations of the same thing. For the correlations, you use this robust EFT approach in which in the limit of MB going to infinity and Q squared is small, you have the relations that I was showing you before among the 4 factors. Optimized observables, as I said, are there, and they have a lower sensitivity to the 4 factors because of the cancellation of the soft 4 factors. Charm loops, this is an important issue. This is very important in the region of resonance where we don't enter. It's a standard model effect that contributes to the Wilson coefficient C9 lepton, depends on Q squared, and is lepton universal. These are the main features of these charm loops. Now, there has been several approaches in the literature to try to estimate these charm loop contributions. One of the first ones are these like constant rule estimates by Kojimirian et al. That we take only as an order of magnitude of the effect, but in order to be the most conservative possible, we allow for the possibility of this long distance to interfere constructively and destructively with the short distance. Okay, if I take the value at face value by Kojimirian, the effect is that the anomaly would increase. But in order to be more conservative, we allow for both possibilities. Okay, this has the implication, because we do that for X amplitude, of enlarging the error bars for the charm loop in our analysis. There are other analyses that has been done in the literature, like the experimentalists try to fit a set of resonances and try to see if the tail of some resonance could explain the anomaly in the region here, and the result of their analysis is that no. And there are other analyses like using dispersive representations and other approaches. In all cases, what we observe is that well and precise computation within the standard model cannot explain this anomaly. Nicely, in the few months ago, there has been a recent update of these like constant rule estimates in which they compute the next leading order corrections, and they found that they are extremely suppressed with respect to their leading order. So in that sense, I'm starting to think that the usual karma that people that does not go through all these analyses says that, well, charm loop maybe is underestimated, should be changed in that probably charm loop is a little bit more overestimated. And the anomalies in this channel that we are observing, they are indeed a bit higher, larger than what we are saying, which is a good news. Now, let me tell you what is the situation about the global analysis. Now, I'm in slide 23, okay? Can you see the guy in the
yes, yes, no problem.
Fantastic. Okay, so I like to put this slide for the following reason, because I mean, there's some people that love one single anomaly, like RK star, maybe because they are simple, the anomaly, and they do analysis focusing on just as a reduced set of observables. I think this is wrong, and it's important to always don't lose the general view. You have to look the general view, the general forest, and in order to get a clear idea of what is the global situation. Because if not, you will probably arrive to wrong conclusions, as it has already happened in some cases. So, in principle, you should first look at the forest. Once you understand the global situation, then you can start looking at the specific observables, but not the other way around. Now, what is our analysis? We do a likelihood analysis, including experimental and theoretical uncertainties, with correlations in the Gaussian approximation. Now, the goal of all this analysis is to determine this CI new physics, and there are 2 quantities of interest: the p-value of a given hypothesis that informs you about the goodness of a fit, and the pool standard model that tells you by how much the standard model hypothesis is disfavored with respect to a new physics hypothesis in order to explain the data. Okay, so the higher the pool, the best this hypothesis explain the data as compared to the standard model hypothesis. Now, inputs. We use all the LFB observables available, RK, RK star, and Q4 and Q5. We use the B2K star mu, branching ratios, and optimized observables, BS into 5 mu, the B2K charge and neutral, the inclusive B into H is mu, BS into mu, electronic modes, and also the radiative ones. We include the data from all experiments, LHCb, Atlas, CMS, Babar, and Bell, whenever they are available. In total, this means 246 observables. This is a forest, okay? Now, I want to insist on that. It's important not to miss any LVB observable. And so an analysis that takes only RK and RK star and miss these two that has been measured by Bell, this is not a complete analysis of an LVB set of observables. And the same way that it's important not to miss important observables, it's also important not to add observables that has nothing to do, like delta F equal to observables, because they would require, if you include them, this would require to include also some extra assumption on new physics. There was a competing group that was including this, and they were going to I would say, wrong conclusions. Now this group has came back from this hypothesis, and now they are not including anymore this hypothesis of including these observables. Theoretical inputs for factors I have already discussed, channel corrections, quark duality violation at high Q square. We use a 10% effect, but there are estimates of the order of 2%. So we are a little bit too conservative probably here. We include the new results of BS into mu from MISIAC, and we include also the charged channel, taking into account mass and lifetime difference, but also annihilation and Hall spectator interactions that are different in one case with respect to the neutral one. Results. Okay, if you do an analysis of just one single Wilson coefficient at a time, that's what we find. Systematically, in all these years, we find that the scenario with only new physics in C9 has the highest pool of 7 sigmas. Then this is the case of the all fit, and the second scenario is the one with C9 equal to minus C10. Well, second no, is another scenario, but with less significance. But if you look at only the LFUA fit, the situation reverses, and there is a preference for C9 equal to minus C10. This apparent contradiction, if you wish, between these two was solved in a paper that we put some time ago, and that I will discuss in a moment. One important thing to say about these one-dimensional fits is that the p-value of the standard model hypothesis, we have observed that it has been decreasing from 11% to 1.4% to 1.1% for the fit all, and from 12.6 to 1.4 for the fit LFU fit. Okay, so this is good, but there is still a long way to arrive to 5 sigmas. Now, what happened in the two-dimensional scenarios? Here, several interesting things has happened. The first one is that due to the fact that BS into mu now approaches more the standard model with the latest number of LHCb, you see that now C10 is consistent with 0 already at 1 sigma. This is a plot of C9 versus C10. But not only that, I mean, more interesting one is the fact that scenarios with Rahan currents like this one, with C9 prime equal to minus C10 prime, now they have a strong significance of 3 sigmas with respect to the absence of them. Okay, so we see really a 3 sigma deviation here in scenarios like this one that from now on we will call hypothesis 5, C9 prime equal to minus C10 prime, and with a C9 muon contribution here. Indeed, this is one of the scenarios with the highest significance. Here you see a 7.4 sigmas. So just to look a little bit more in this scenario, we wanted to know, I mean, what data prefers. If it prefers for the left-handed side coupling, a vectorial coupling here, or an SU to left coupling. And clearly data prefers a vectorial coupling for the left-handed side, as you can see, for this difference of near 1.5 sigmas. Finally, concerning the 6-dimensional fit, what we observe is a systematic reduction of the pool, increase of the pool from 5.1, 5.8, 6.6, and quite a coherence and stability even in the central values. I mean, the ones that are smaller still tends to change a little bit, but we start seeing stability. And that's very important to get the global final picture. Now, what I was telling you before about this problem about LFUA fit preferring C9 and, preferring C9 equal to minus C10 and the all fit preferring C9 was solved in that paper where we introduced the idea that maybe we are observing not one type of new physics, but 2 types of new physics. One which is LFUE violating, and that explains RK, RK star, and Q4 and Q5, and one which is a common new physics to all charged leptons. This is what we call CIU. Same for electrons, muons, and taus. Indeed, what you observe is if when you do the fit to C9 and C10 in the all fit, you see this is the best fit point or best fit regions, or the confidence regions, and this is the corresponding ones in the LFUE fit. So you see some tension. On the contrary, in this scenario 8, in which you have C9V equal to minus C10V and C9U, you have a perfect agreement between the two degrees of freedom and a higher significance of 7.3 sigmas. But not only that, it's very nice that if in the future you observe also large deviation in BS into tau tau, and I will come to that in a moment, that could be connected with RD and RD star, then you can naturally generate a universal contribution to C9. Okay, this will be by closing the loop of BS into tau tau. Now, talking about consistency, I think that that's a very important plot, and see the evolution of this plot. Here you have the two. Now we're looking at the trees. Okay, I have already looked at the forest. Now I can look at the important trees. The important trees are P5 prime and RK. And what you observe is that these two scenarios, the scenario with right-handed currents that I call hypothesis 5, and the scenario with LFU new physics that I call scenario 8, they have a very good explanation of both anomalies. The case of C9 starts to be a little bit on the edge for RK, which is good. It's good, really. I don't think that C9 is the last answer at all. It should be the last answer more near to this kind of scenarios here. Also, then scenarios like C9 equal to minus C10 that many people like, they are too naive, and as you can see, they are very far away from explaining, for instance, P5 prime. This is one important point that I would like to insist here, and is that we observe that the role of the right-handed currents that makes this scenario work so well is to counterbalance the effect of a large C9. So what it does is, indeed, the right-handed currents approach the result to the standard model for RK in such a way that you are in much better agreement. Okay, so it's important. There's a count of two directions. C9 goes in the direction of more new physics. Right-handed currents moves in the direction of standard model. Now, this connection between BS into LL and B2C L new anomalies can be done using an SM-EFT. I will be very brief on that. You have two operators with left-handed doublets, this O1 and O3. The flavor changer current part of the operator O3 describes the charge anomalies, and the flavor changer neutral current part of the operator O1, O3. If you impose this constraint that C1 and C3 are equal, then I can explain you the anomalies in BS into LL, but it has a byproduct, because by doing this, that you do that in order to avoid the constraints from B to K star nu, ZK, and direct production. By doing that, the byproduct is that you're putting together a tree level and a loop level process. And as a consequence, BS into tau tau gets a huge impact in such a way that the C9V tau and C10V tau is enhanced by some orders of magnitude. As I was telling you before, because of this BS into tau tau large effect here, you automatically can generate a new physics contribution, which is of the type of universal. Now, if you put all the things together, not only the BS into LL anomalies, but also RD and RD star, in this particular scenario 8, this C9V equal to minus C10V and C9U, what you find is that the best fit point without RD and RD star and the best fit point with RD and RD star in this scenario are very good agreement. And indeed, the global pool, in that case, pool standard model, becomes 8.1 in this particular scenario. The best fit points move a little bit, but they are quite close to the ones that you have without RD and RD star. So that gives you a very nice global picture. Of course, you will detect this if you see a large effect in the branching ratio of BS into tau tau or B2K tau tau. Now, summary of the dominant scenarios. These are the three main scenarios, C9, the one with LFU new physics, and the one with right-handed currents. Now, the next question is for the future. Can we disentangle these two interesting scenarios? And the answer is the following. If you look at here, at this plot here, in RK, you cannot disentangle them. You see that they are quite close, so it's impossible that you have enough precision to disentangle them with RK. With RK star, you cannot, because of the problem of the hadronic uncertainties in presence of new physics that you can see here clearly. But Q5 can. This orange is the one with right-handed currents, and the gray is the one with LFU new physics. And here is a standard model for Q5. So if LHCb is able to measure with enough precision of L2, this observable can disentangle which is the best or which is the scenario selected from these two. So Q5 will bring a very important information that RK and RK star cannot. Okay, so this is our outlook. Okay, look at Q5, look at if Q5 is large and positive, and this would favor the scenario with a large negative C9 and right-handed currents. If instead you see a large BS into tau tau, that would favor the scenario with LFU new physics. Now, possible candidates. Well, you can have a vector leptoquark SU2 singlet. That's one of the most preferred candidates. It's coupled to third generation. It explains both charge and neutral anomalies, has the right pattern. There are no true-level effects, and is no in conflict with direct searches. That's a particle, okay? But then you have to put that inside a UV completion model, and that's much more complicated, okay? Here I'm giving you just some examples of attempts to put a leptoquark of these characteristics inside models. Besides that, if you focus only on BS into LL, you can use different translations of Z-prime models that could explain anomalies there, okay? And finally, you can have much more elaborated models like this Patisalam to the cube, in which you have a TEP leptoquark associated to the third generation. Now, finally, what else? What else? So what is the next step from my point of view? Here I will be very brief because I had to remove several slides. So first of all, if you have enough precision, you can start looking at the massive observables like M1 and M2. We have analyzed them. They enter in here in the angular distribution. I'm not giving you here the explicit expressions. You will see it in a paper that will be posted very soon. We observe that M1 is basically insensitive to most type of new physics, at least the most interesting ones. And M2 is sensitive only to scalar and pseudoscalar new physics contributions. Indeed, if you have an extreme but possible pseudoscalar contribution here, which is this green band, you have some chance to disentangle from the black one that corresponds to the standard model. But of course, this would require precision. But besides that, more interesting thing is the fact that you are opening, and this will be in this paper that will appear probably in 2 weeks, a new set of S-wave observables. So the angular distribution contains the P-wave piece that I have been discussing up to now, but also an S-wave piece that comes from a K0 being a broad scalar resonance. These parameters that up to now were taken as nuisance parameters now will become signal for LHCb. Here I'm giving you the definitions of these new observables, new S-wave observables, in terms of these complex vectors, okay? For the real is because you have bilinear products of real parts, and the imaginary because you have imaginary parts. Now, the next question is what do we learn from these S-wave observables without using information on poorly known for factors for the S-wave? And the thing is that you can rely on symmetries to get a very interesting information. The information comes basically between because of the fact that the number of coefficients that you have in the distribution and the rank of the matrix, the rank of this matrix here, which is the gradient of the coefficients of distribution with respect to the amplitudes, is different. Sorry, is different. I mean, the difference between these two numbers, because they are non-equal, will give you a certain number of relations. I'm not going to tell you here how we derive these relations because this is a long thing. But what I'm going to present you is what information we can extract from these relations. And a very nice information is that we obtain very strong bounds on the size of these new observables. And this bounds comes from these expressions here that you find using only the relations. And they tell you that these observables S2 and S5 should be smaller than 0.14, and S3 and S4 should be smaller than 0.22. They are very, very strong constraints. Moreover, we can also construct other observables, combination of these S-wave observables, that they are chosen in such a way that they can be predicted out of the P-wave observables. So here I'm giving you an example of this new observable W1. In the standard model is the gray boxes, and these red and green ones corresponds to these interesting scenarios. So you see that already from these wave observables, you can also get information on these interesting scenarios. I will not go into any more detail on that. And then let me just finish my talk very briefly with this new anomaly. This is an anomaly in a different sector. It's an anomaly, up to now I have been talking all the time on semileptonic anomalies. This is a non-leptonic anomaly. And let me tell you what is the parallelism that we have done when analyzing this. In the semileptonic case, you construct observables, optimized observables, by canceling sub-4 factors, like in P5 prime, or by doing ratios, or branching ratios. Ratios to the second generation leptons versus first generation leptons. In our case, the optimization will be to write down an observable in terms of longitudinal amplitudes. You will see, you will understand in a moment why optimizing means focusing on longitudinal amplitudes. And the ratios will be ratios between transitions to second generation quarks versus transition to first generation quarks. On the left, you have lepton flavor universality. On the right, you have U-spin symmetry. This is a kind of parallelism between the two types of anomalies. Now, why I'm saying that optimization means to focus on the longitudinal amplitudes? The reason is that if you have an initial spin state 0 that decays into two vector mesons, the two vector mesons can be in a analytic state 0, minus, or plus. Due to the B minus A structure of the standard model, this amplitude dominates. And in order to have the two in an analytic state minus, you need a one-like quark LST flip that costs you a power suppression. And in order to get the I plus, you need two power suppressions. Now, and here is the main point. All these non-leptonic decays are afflicted by infrared divergence, weak annihilation, and high spectator scattering. The point is that since they are power suppressed, these infrared divergences, they enter a leading order because of what I just explained here in these amplitudes here, but they are subleading in the amplitude A0, in the longitudinal amplitude. So the point is, can we construct an observable out of only this longitudinal amplitude? And the answer is yes. And this is this observable L, which is function only on the amplitude, which is function of the branching ratio and polarization fractions. I'm not going to enter into any detail here. Let me just give you some general ideas. The point is that the experimental value for this observable is given here is 4.43 plus minus 0.92. And our standard model prediction, including next to leading order Q factorization corrections, is this one. So there is clearly a tension of 2.6 sigmas between the prediction and the measurement. Again, nicely, what we observe is a deficit in the B2S versus the B2D, as the deficit in the decay, in the semileptonic case, of second generation versus first generation. More than that, if you want to identify what is the main operator that drive the effect, we were able to identify this operator, and this is the operator Q4S, which is given here, and Q8GS. In the case of Q4S, with a 25% contribution with respect to the standard model, you are able to explain this anomaly. Okay. In the case of CI, you need a 100%. It's interesting to notice again in this kind of anomaly, in this kind of parallelism that I'm trying to tell you, that in the case of the semileptonic anomaly, also C9 gets around 20 to 25% contribution with respect to the standard model. By chance, maybe. Now, if you want to just to motivate this, if you introduce a model with a Kaluza-Klein gluon, axi-gluon, you would be able to explain this anomaly. These are the couplings of these Kaluza-Klein gluons to the down quarks, and there is another Lagrangian with the couplings to the flavor diagonal quarks. Now, these two couplings of the Kaluza-Klein to the down quarks are constrained by delta MBS, and moreover, they enter in this way inside the Wilson coefficient C4S. We need to assume a flavor diagonal structure of the coupling of the Kaluza-Klein to the first two generations to avoid the problems with K and demixing, but also to avoid constraints from these digit searches. Now, when you put all the things together, LK star, K star, and delta MBS, you realize that for this, let's say, illustrative model, you need quite a bit of fine-tuning in order to put in agreement LK star, K star with delta MBS. Okay, you need a fine-tuning between delta left SB and delta right SB. And finally, that's my last slide. If you would like to try to connect this with the BS into L anomalies, if you insert this Kaluza-Klein gluon inside a spectrum of a composite X-dimensional model and you include a Z prime, the Kaluza-Klein gluon would explain the LK star K star with a diagram in this way, and the Z prime will explain the BS into L anomalies. So let me move to the conclusions. We have observed for the first time in particle physics a large set of coherent anomalies that all point in the same direction. We have increased the global consistency. We observe an increase in the pool and no change in the hierarchy. And we observe three dominant scenarios. C9, that basically rule out any scenario that does not include this kind of contribution, the possibility of right-handed currents, and the possibility of LFU new physics contributions that, moreover, can be connected with the charge anomalies. For the future, it's important, besides updating B2K star mu and including these newest wave of observables, to measure BS into tau tau, because this will tell us information also about the scenario with LFU new physics, for the reason I was discussing before, but also to measure Q5, because it's the only one that can disentangle this right-handed coordinate scenario with AC9 versus the scenario with LFU new physics. And finally, I have presented you a promising new B-Flavour anomaly in the non-leptonic sector that shows a 2.6 sigma tension with respect to the standard model, and we have identified the coefficients and proposed a one first possible model. Let me finish with this, which was inspired by Arthur Conan Doyle. Thank you very much, and sorry for the horrible technical problems.
Hey, thanks a lot, Kim.
I hope that you are not still in Transparency 25.
No. We'd have told you. So let's open now the time for questions. So please, people, if you want to make a comment or question, you may like to raise your hand or speak up.
I have a question. This is Bernardo Adeva. May I?
Yes.
Yes, please.
So Kim, I was concerning this. My question concerns this latest observable, the L K star, right?
Yes.
So it's I think it's very good news that in this observable, the hard gluon, the weak annihilation, even the form factor uncertainties get reduced. But yet the uncertainty coming from the direct ratio PD, the direct ratio between the two penguin contractions dominates the theoretical error. That is still 25%. So I wonder, I mean, why this is the case. I mean, this ratio seems to be difficult to, the SU3 symmetry breaking seems to be difficult to describe. I wonder what are the perspectives for improvement of this 25% error. I mean, whether lattice QCD can help, whether chiral perturbation theory can help.
That's an excellent question, Bernardo. That's the right question to ask on this part. Of course, I didn't have the time to go into the details of the atomic uncertainties there, but that's the right and important thing. So I was insisting first that in this observable, you have the two types of uncertainties. You have, indeed, I have not insisted much on the form factors in a way. There's one of form factors and the one of infrared divergences coming from this weak annihilation and also the spectator scattering. Now, what we observe, and that's the reason why we construct the longitudinal amplitudes, the observable in terms of longitudinal amplitudes, is to have these second ones, power suppressed. Because if not, that would be the dominant one. Okay, that was the first step, was to take them in the longitudinal one because they are power suppressed, and this allow us to have good control. Indeed, in the paper, you can see the size of the effect of these power suppressed infrared divergences, and they are quite smaller compared to the one of the form factors, as you are perfectly pointing out.
Right.
Now, why the one of form factors are large? Okay, the reason, and there's a clear reason. I mean, in my talk that I give in Morion on that, that was a kind of a, how to say, to motivate people, was that we could not take the correlations included inside the two form factors because the ones that were doing this calculation were not providing us these correlations, because in particular they didn't consider them yet. So in order to reduce this uncertainty, the next step is to include those correlations. So and for that, our plan is to talk with people doing Lycons and rules, and sit down with them and get these correlations and then put it inside the L observable. And I'm convinced that then this 25% will reduce substantially. Okay, so it's correlations. The answer to your question at the end of the day is correlations.
Correct.
And this is now in our to-do list. I mean, I would say it's the first in our to-do list. Then the other important thing that we try to motivate is that other people try to construct other models that could explain this, and nice if they could be related with the ones of BS into LL. But the first important thing is to solve this issue of the 25% coming from correlations. And once we have that, okay, this 2.6 sigma, I don't know how large will become. So,
good, very good. Thank you. So because the experimental measurement is very clean indeed.
Yes.
And certainly statistical error will be reduced soon, and also systematic error. But of course, that error we are talking about drives the significance of the new physics. Okay.
Absolutely. We put it in black in a way. I mean, we say as the main message, one of the main messages of this is that's the direction to. If you read the paper, is written very explicitly that that's the direction to improve, to have a control on this. And the first way to do it is first correlations, but if you want also more precise determination of the four factors themselves. So both things. But already from the correlations, we will have a first step. But so we are working on that. So I mean, it's in our table. Thank you.
Okay, thank you. So I see another question by Herman.
Hello, Kim.
Hi, Herman.
I have two questions. Because you said that the cancellation of the soft four factor occurs at leading order, but at the level of precision that we are reaching now, maybe higher order corrections might start to be important. Is there any study of the importance of these higher order corrections?
Okay, so can I answer this question and then you answer the second one? Or
the second one is very simple. I mean, what are the order of magnitude of the masses of the Kaluza-Klein and the
okay. So for the first one, I had doubt to put this in the talk, just not to create a confusion on this. The soft form factor information is only used to construct the observable. Okay, it's only used to construct the observable. So we construct the observable in such a way that this soft form factor is cancelled at leading order. But if you look at the same slide, I was writing below, this is not the way we compute things. I mean, we compute with the soft form factor, but then we include alpha S corrections from Q's factorization, alpha S non-factorizable corrections, long distance charm contributions, and short distance charm contributions. So, I mean, all those next to leading order corrections are included in our analysis. Okay, so the soft form factor is only used to construct the observable, right? But it's only the first step. I completely agree with you. I mean, the leading order is not enough now. Now we are in a precision era that you cannot work with that. So all the power corrections has to be included, and they are included in our analysis, and they are the bulk of the effect. And around the second question is around the TeV scale. This Kaluza-Klein gluon.
But then you should see them in the LHC. You have something in the TeV?
It's 2 TeV. I think it's 2 TeV. It's 2 TeV.
The TeV you should have. You should see something in the LHC.
Yeah, I mean, we have looked at the constraints, at the direct search constraints, and it's not yet possible to see it. But okay, a full analysis with tails of this possible Kaluza-Klein, this is not done. So that could be a possibility. Still, I was insisting on that this model to me is just kind of a motivation model. Okay, I'm not sure if we can consider this as the final model to explain this anomaly. I would say that this is just something to motivate others to into more elaborated models that maybe require also less fine-tuning and also can nicely be connected with BS into LL anomalies. Okay, so but this is something that I agree with you. Should we look in more detail in a more complete analysis, looking at possible tail effects? Thank you, Herman.
Okay, thanks.
Okay, thank you. So I see Carla also raising her hand.
Yeah, thank you. And yeah, thanks, Kim, for the thanks for the nice overview of these anomalies. I have a curiosity because you explained a bit all the different observables that you include in these global feeds and also the compatibility between some of them. So something I was missing is the angular analysis of BS to phi nu mu. So far, it was not very precise, but you might be aware that there is a very recent update of this. And I was wondering if you have been able to check already any compatibility between these results and the rest of the observables.
Yeah, indeed the branching ratio of BH into 5 mu and the optimized observables of BH into 5 mu are included in the analysis. But the very latest result came out after our after our analysis. This always happens. Yeah. No, that's very interesting. And my impression, I mean, since we have already included this, and what you see is again a systematic deficit with respect to the standard model. But I mean, it has not changed substantially the situation. I would expect a slight increase. Maybe now we are at 7.4. It could maybe go to 7.6, but not more than that. And of course, and there will be no change on any hierarchy. That's completely clear. But I agree. I mean, the very latest. I mean, come on.
I was just curious if you had checked. I understand, yes, that the direction of the data is kind of compatible with what we think is that mu.
Absolutely.
And yeah, I was wondering more about the size of the deviation, because there we are still, I think LHCb did actually kind of just a one-dimensional fit of C9, right? And the direction is kind of similar, but of course the deviation seemed smaller. Of course, we have more limited stats. So I was wondering if you had been able to look into this a bit more, but I totally understand that this is very recent.
Yeah, no, this plot is from that. Exactly, this plot is from that. Okay, the only thing is that we have included in our analysis the crosses in gray. Okay, this is the ones that we have included, because this is the one that we include in our because I mean this.
But this is for the branching ratio even, right?
Yes.
Yeah, no, there's also an update of the angular observables as well.
Okay.
Yeah.
Okay, okay. The one of the angular observables,
I think it was presented only 2 weeks ago at FPCP. So
this one I have. Oh no, this one I have not checked. That's very nice. Thank you very much. This one I was not. I mean, I had a nightmare of May and June, and I missed that once. Okay, thank you very much. No,
okay, fair enough. Yeah, just curious to see how things look there.
So it's public. There is a paper in archive.
No, not yet. It's just presented at the conference, and the paper is like for the branching ratio is in preparation, so it will be out hopefully very soon.
Great. No, that's fantastic. I mean, the more data we need and the more coherence we observe, that's very good. There is also another channel that I think that you analyze also, which is the lambda decay, the semileptonic lambda decay, and also it has been solved the problem that was at high Q square, that now is much more coherent with all the rest. And there was a problem with the ratios of the
normalization mode, yes, and the production fractions, yes.
That's also important, and that's also very good news. So I mean, I always say, I mean, it's the last sentence of the talk, no? I mean, or we're seeing new physics, or in a way there is a brutal conspiracy among all those observables that it cannot be. It can be. If you would have just one observable, like it happens with the ghost, the diphoton thing, then fine. But this is not the case. I mean, we are in a different league. So thank you very much, Carla, for this information.
Okay, thanks a lot. Any more questions or comments? I don't see anybody raising hand. Yeah, Maria Jose.
Yeah, thank you, Kim, for this very nice talk. So I was wondering if you could elaborate a bit further on this measurement from CMS that was in agreement with the standard model. And you said that it was a different treatment of the PDF. And
yes, there was a little bit of I was hesitating to put it or not put it, but you know, I'm always a little bit provocative. So if you know me, I like to put these things. So the point was the following. In here I'm putting only LHCb, but there is another plot in which you will have LHCb, Bell, which is in perfect agreement with P5 prime, with larger error, of course, and then Atlas, which has even larger errors. I mean, has very large errors, but also there they see clearly an anomaly there. But one of the experiments, which is CMS, seems to be more near to our standard model prediction. Okay, and some people were saying, okay, this means that the anomaly there has disappeared and there was some problem in the other experiments. No? So that was already some time ago. Right? So I was very much in contact with the person that was doing the analysis, because they invite me at the very beginning when they start the analysis, and I explain all the features. At some point we disentangled because they had to do the analysis, and then when they present the analysis, I was kind of surprised. That was in Morion, and I was nearby to Adrian, that was the person in charge of the Atlas analysis. And the first thing that surprised me is that CMS extract the correlations of FL from one PDF and the correlations from P1 and P5 prime from a second PDF, different ones. While all other experiments, they take it from the same PDF. And that's really very important, because they are the correlations among these observables, and FL is inside also P1 and P5 prime. So if you extract wrongly these correlations, then you can arrive to the wrong conclusion. And the problem is that it seems that contrary to Atlas and Bell and LHCb, they had some instability problems and they were not able to extract it, as let's say, correctly from the same PDF. Okay, so they make some kind of Monte Carlo tools, Monte Carlos to try to extract this and then plug it inside. Okay, which is kind of delicate. But the other thing, and this I was not aware, and this was given, it was Adrian who told me, is that he was talking with the person doing analysis in CMS, because he was responsible for the Atlas analysis, and he discovered that in CMS, instead of using the analytical integration of the three-dimensional PDF, they were using numerical raw fit. Of course, in principle, you can think, okay, I can do it, and because I mean that's much faster. But according to Adrian, this raw fit has problems with three-dimensional PDFs. You can trust it up to 2 dimensionals. And these guys from CMS were not aware of this problem. So, I mean, this you can do it always, the analytical integration, as Atlas, Bell, and LHCb did, but it's cumbersome, it's long, but all of them, they did it. And it's much safe than using a the numerical raw fit. I don't know if they have redone it again using analytical integration or not, but that's our suggestion for the next analysis. Do this and do this in order to make sure that we are comparing the same things. Okay. I hope that this answers your question.
Yeah, thank you. So then the measurements are not compatible with the PDF associated uncertainties then, or?
No, what CMS finds is, the error, of course, are large. It's not like LHCb, which has a very tiny error bars. Yeah. But the result is compatible with the standard model and with new physics. Okay, but is the one which is closer to the standard model as compared to all the other ones. Mm-hmm. So it's very important to make sure that you have full control. There is also some other things about backgrounds that I will not enter and that Adrian told me that also should be also analyzed in more detail for CMS. Okay.
Okay. Thank you very much.
Thank you very
much.
Okay. Thanks a lot. I don't see anybody else raising hand. Okay, so yeah, given this, thanks a lot, Kim, for this nice talk.
I'm sorry again.
Yeah, sorry to all of you for these technical problems. So it took a little bit longer than usual, but this is not your fault. So thanks everybody for connecting. So the next seminar will be after summer, so in middle of September. It's going to be about machine learning, and we will inform all of you in due time. But until then, yeah, wish you good summer, and we meet again after the break. Thanks everybody, and thanks Kim. Bye-bye.
Thanks Kim.
Thanks.
Bye. Thank you everybody.
Thanks.